I'm really happy to announce Johannes Anschütz from University of Bonn. He will tell us about Pro-etale Cohomology of Rigid-Analytic varieties.
Yeah, thanks a lot for the invitation. And so let me start by clarifying the setup. So P should be some prime. And then C over QP should be a non-Archimedean, algebraically closed extension of QP. And then X over C should be a smooth rigid analytic variety. And I want to assume that it's of dimension D. And moreover, I want to consider some pro-etale QP local system. On the pro-etale side of X. What is this pro-etale side? So it's basically a side of all perfectoid spaces of a pro-etale map. So I actually take the big side here. So I consider all perfectoid spaces T with X, T over X together with a pro-etale topology. And then I spoke about QP local systems. More precisely, I should underline it because QP underlined here refers to the sheaf given by ascending a perfectoid space T to the continuous homomorphism of the underlying topological space of T to QP. And then the question which I want to use to motivate this talk is if there exists a version of Poincare duality for the pro-etale cohomology. So is there some sort of perfect pairing? Of the following. So should be a pairing between pro-etale cohomology with coefficients say, in the dual local system and then appropriately twisted and shifted, tensor with a theory of compactly supported pro-etale cohomology with coefficients in L, and this perfect pairing should have values in QP. And so I want to add here that this question in particular includes the question for a good theory of this compactly supported pro-etale cohomology. So I now want to discuss several examples which motivate this question and indicate results which are known. So the first example is based on work of Mann and Gabbard-Saffialo. And so in this example, we suppose that X is proper and L is a trivial local system. And then in this case, the second question is obsolete because the compactly supported cohomology should just agree with the usual cohomology. And so then it's proven, actually this was proven also by Scholzer. So when the Pro-etale cohomology groups, which in this case are actually in this case are actually isomorphic to the inverse limit of the etale cohomology groups with solutions in Z mod P to the n, and then one over P. So that these are finite dimensional.
So to identify with this, you still need finiteness from mod P to the n.
Yes.
Otherwise, it would be clear that it is like the continuous cohomology like Janssen, 1 over P, but in fact, everything is finite. So the new one is 0.
Yes. So actually, this equality here, or better isomorphism, is a non-trivial assertion that these are also finite. Yes, that might be. Okay, but they are finite dimensional and also duality whole. So we have a perfect pairing. So between the ith cohomology group Q, and then it's paired with the 2D minus ith Pro-etale cohomology group with QP coefficients. But actually, the same statement also holds true for certain local systems. Namely those if L, the QP local system admits a lattice, so it of the form L0 and 1 over P, where L0 is the ZP local system. Okay, so this statement, although I mean it's a very difficult theorem, but it's in its statement it's not surprising. And so this is why I want to move to example 2. And here, this I learned through Lebras and then Colmes, Gilles, and Messiol. And it's much more instructive. So I consider now the rigid affine line, so it's not a fancy space. And I also don't consider any fancy local system. And in this case, the Pro-etale cohomology with QP coefficients, it's the following. It's QP in degree 0. That's no surprise. It's 0 for I greater or equal than 2, but something happens in degree 1. And there it's isomorphic to the global sections of differentials omega 1 on x, which are isomorphic to OX modulo the constant. And so also, that's the result for the Pro-etale cohomology, and now the one for the compactly supported cohomology. And here the result is that it's 0 if I is not equal to 2.
How you define the compact support cohomology? Is it done by doing torsion coefficient? No, you cannot. You just use kind of pieces of the relative to some pieces of the quasi-compact pieces or the direct limit?
Yes, and I want to write it here. Okay, and so what's the outcome? So we get QP in degree 2, and then another contribution, which is the stalk of P1 over C at infinity. So the stalk of like holomorphic functions at P1 of the rigid-analytic if I is equal to 2. And so now I should define what the compactly supported cohomologies are. And so here one can profit from the fact that X is a Stein space, meaning that it's like an increasing union of balls here. And so this allows the following definition. The compactly supported cohomology is the colimit of over all U inside X quasi-compact and open of the fiber of a morphism of complexes. So R gamma X Pro-etale QP to R gamma X R gamma X without the closure of U and then coefficients in QP. And so here what's happening, so X without this closed subspace is obviously an open subspace, and therefore it's again a rigid analytic variety. It has its pro-etale cohomology. So this makes sense, but usually you would not define, if you want to have some sort of excision sequence, the compactly supported cohomology in this case. But what makes this definition good in the Stein case is that actually you could also that the quasi-compact opens and their closures are formed to cofinite systems, and so therefore in the colimit this does not matter. Okay, and so this example is very instructive, I think. And so why? So the first thing to note is that these spaces appearing in degree 1 or in 2, they are infinite dimensional. And another thing, which one can also see by looking at the description, is that they have some sort of coherent flavor. But it's not literally coherent because they want most of the constant functions there. And this formula here, one should better write here the closed differential forms and so on. Anyway, so one has this coherent flavor. And what's a very remarkable observation made by these authors is that a duality still does hold. Namely, the space here of differential forms is dual to that additional piece that one also sees here. And so therefore the duality, what happens is that the QP in degree 0 pairs with the QP here in degree 2, and then this PC in degree 1 pairs with this piece in degree 2. But that's another, I think, surprising feature, namely the degrees, they behave different. One does not pair an H1 with an H1. So and so what's also remarkable is that these three authors, I just confirmed it, they can also prove that statement for X a general Stein space of any dimension. Meaning they can prove perfect pairing here in a suitable sense.
Do they have problems with non-separated things, or they Do they have to work in some derived, fancy derived setup, or you have just
Everything is separated. But one can also see that they have to use at least some fancy stuff, because with duality, it should also incorporate the some topology on the omega-1 or that thing. And so one sees that one also should view better these Pro-etale cohomology groups as some topological. So one needs functional analysis. And then another thing which I did not mention, I mean, the space is A1, and it's a A1 in characteristic 0, and the coefficients are of characteristic 0, but still it's non-trivial. So that's also a surprise. And it also says that there does not exist excision or the Pro-etale cohomology. So, but the excision does hold modulo for FP coefficients, and then from here one can also deduce that the R gamma of the affine line with ZP coefficient is just isomorphic to ZP0, so ZP in degree 0. And so therefore also this formula that I've written here is just false. Okay. And so then one can wonder, like, what makes this Pro-etale cohomology with QP coefficients different, so that one has these surprising cohomology groups. And so
this excision you're talking about looks like homotopy property. What kind of excision property you?
Like, I guess I should write compactly supported cohomology, and then one would like to have an excision sequence for relating the cohomology of P1 with compactly supported cohomology on A1 with the complement, which is infinity. But the Pro-etale cohomology of infinity as a point would just be trivial.
Ah, yeah, okay. Got it. Okay.
Okay, and so what can be seen as an attempt to some explanation is that one has interesting sheaves on this Pro-etale side, which do not come from etale sheaves. And so what is an example for such a thing. So the whole talk is placed in a p-adic context, and then what we can consider is the p-adic logarithm. So the p-adic logarithm can be made into a morphism of sheaves from the 1 plus an open unitist mapping to A1 over C. So more precisely here, the OT is the sheaf which maps some test perfectoid space T to O T. Then we have the logarithm here, and the kernel of the logarithm is an etale sheaf, which is QP mod ZP takes just 1. And so now what one can do, one can pass to the inverse limit over the multiplication by P on this sequence of abelian groups. And so what happens is that one gets here just this inverse limit over multiplication by P. That's an isomorphism here, so that's a morphism to A1 of C. I think I better call it O. And so what is the kernel? The kernel, if I consider multiplication by P, on the Pro-etale side will just be QP1. Okay. And as I'm working over C, the state twist actually does not matter. So this is calculating QP. And so this exact sequence, which can slightly be thought of as a version of the Artin-Schreier sequence, like the Artin-Schreier sequence, also yields that the cohomology of A1 over Fp is non-zero in higher degrees. And so similarly, one can attack this calculation by using this sequence like this. And so one sees that here the Pro-etale QP cohomology gets a contribution from the cohomology of O. Okay, and so now one has to pair that sequence with another feature of Pro-etale cohomology. So if we consider the morphism of sides from X Pro-etale to X etale, then by calculation of like Schulze following Faltangs, one knows that the R nu lower star of O, so of the sheaf on the right-hand side, is isomorphic to the tail-twisted I-forms on X. And so therefore, one sees that this contribution in degree 1 in the Pro-etale cohomology here actually comes from the first cohomology of this sheaf O. And for another thing which is interesting is that this example here in the middle is a prototypical example of a Banach-Comet space. So it's an extension of a QP space by the structure sheaf O. Now I want to move to a third example, which I learned through David Hansen, and it's also instructive. Again, I consider not a fancy space, the rigid analytic P1, but now I want to consider some non-trivial local system. And so this local system will not have this property that it admits a ZT local system as a lattice. And then I get some surprising results for the Pro-etale cohomology. And so this example will be constructed using the Gross-Hopkins period morphism. So let me just fix. Yes. So what we do is we fix a one-dimensional formal group G0 over Fp bar, and which is of height 2. And then we let M be the rigid analytic generic fiber. But we'll Lubin take deformation space. Over OC. And so, in particular, if one considers the C points of this rigid analytic variety, then this parameterizes pairs G rho, where G is a formal group over OC, and rho is some isomorphism with a framing object. So more precisely, it's actually like a quasi-isotony. And between the framing object G0 base change to OC mod B to G base change OC mod B. And so now, given any such pair, we get the following. So, first of all, the Dieudonné module of G0, 1 over P, just by means of its quasi-isotony, isomorphic to the Dieudonné module of G, 1 over P. And so now the Dieudonné module of G has a canonical surjection, at least after tensoring with C. To the Lie algebra of G 1 over P. So this is a free rank 1 module over OC, and then they change to C, and this receives a surjection from there. But when sending such a pair of G and rho to exactly this quotient of G0 tensored to C to the Lie algebra of G, this defines the Gross-Hopkins period morphism from M to P1, which was the space X. And so now we have some natural ZP local system over this rigid analytic generic fiber. Namely, we can just take the P dictate module of G. And so now the observation is this local system. So let me call it A0. So this is a ZP local system on M with fiber the P dictate module. This local system, if I rationalize it, it will actually descend down to the projective line. And then the calculation function is about the Pro-etale cohomology groups of L. And by the same methods, one can then also calculate the Pro-etale cohomology of the dual and so on. And then also check the duality statement that was motivating this talk. But
just down there, the Dieudonné module theory that you use is the MG and so on. This is the characteristic P Dieudonné theory, or because G is over which kind of Dieudonné theory you use? Theory for the fiber over the residue field, yeah, or something else.
No, like over OC mod P. Over OC mod P. Okay. G is a formal group, it's actually so P divisible, and it's a formal group over, say, OC mod P, and there I can consider the covariant crystalline Dieudonné module, which would produce a module over A crys, but this module I can also base change when to C.
Okay.
Okay. And I wanted to give a name. This local system, I call it LT, and the cohomology group here are calculated to be the following. So it's 0 in degrees not equal to 1 or 2, and it's a BC space of dimension 1 and minus 2 if I is equal to 1, and it's a BC space of dimension 1 and 2 if I is equal to 2. And so I have to explain what the BC space is, and for this I want to go back to this short exact sequence here. So looking at say CP at C-valued points, one can BC space is like an extension of C by QP. And so BC space is now a generalization of this. And so in particular, a BC space has two different contributions. So it has a contribution of the numbers of copies of QP, which is actually the second one, which can also be negative, meaning that the QP is modded out. And it also has a number of copies of C. And so in particular, if that number here is positive, then that space is infinite dimensional. And so in particular, this calculation indicates that the Pro-etale cohomology is just not finite dimensional. Okay.
Is that two? Is the rank Dubné module?
Pardon?
Is the two related to the rank of the Dubné module?
Of the height, yes, exactly. And so and this calculation can actually better be understood using the Fargues-Fontaine curve.
So here you BC space is a functor on perfectoids and you change the test perfectoid, or this is just, so in which sense is the cohomology equal to BC space that
Okay.
you cross with test perfectoids or not?
No, what I do, like I said, that one should consider the Pro-etale cohomology not just as an abstract QP vector space, but what is better is to consider the push forward to the Pro-etale side of sparse C. And then the BC spaces embed into Pro-etale sheaves on sparse C. And so therefore, one should view this result as that this push forward produces a BC space of that correct dimension. And then the Pro-etale cohomology just identifies with the global sections on the Pro-etale side of sparse C of these Banach-Hermes spaces.
And you know that this contradicts the theorem by Kedlaya and Liu.
So it was already a mistake to observe by Schultz in 2017.
Yes, so what I want to speak about now is that one should better view this calculation using the Fargues-Fontaine curve. So, and I want to recall shortly how this is defined. So, Fargues-Fontaine curve for C, it's the quotient of the space YFF modulo the Frobenius, and the space YFF. It's the star of the width vectors of OC flat, and then I remove the log of Teichmüller of some pseudo-uniformizer times p is equal to 0. And the space also comes equipped with a T divisor, usually the inclusion of which is called I infinity. And it corresponds to the until C of C flat. And so we have a functor from isocrystals over Fp bar to vector bundles on the Fargues-Fontaine curve for C. And so the functor is not difficult to write down. Namely, so what is an isocrystal? So it's a finite dimensional QP-label vector space. And phi is a phi linear automorphism. And to such datum, one can associate a vector bundle just by descending a tribute vector bundle on y of f modulo some descent datum. And this descent datum can just be given by the x block phi. And so, for example, what we get is a vector bundle O1/2, and it's the image of like the isocrystal of a simple isocrystal of slope -1/2. And so this simple isocrystal of slope -1/2 in our situation, it just identifies with mg0 and then rationalized with the given Venus coming from Dieudonné theory. And so the way I mean the sentence that this can be better understood using the Fargues-Fontaine curve. So what do I mean precisely by this? So we take this Pro-etale cohomology that we are interested in. And this Pro-etale cohomology should be viewed as the cohomology of some complex on the Fargues-Fontaine curve. For some complex A T of coherent sheaves on the Fargues-Fontaine curve. Now the nice observation by Hansen, at least I learned through him, is that this complex can be made explicit. Namely this complex LAT. Like it's constructed out of like Dieudonné theory for p-division groups over integral perfectoid rings. And then one ends up with the following. So one can ALT is the fiber-morphism of complexes, and these other two are given by the vector bundle O1/2 tensored over QP with the Pro-etale cohomology of P1. So by the first example I explained, this is just isomorphic to Q plus Q shifted by 2. And then there's another term, which is I infinity lower star of R gamma of P1 acting on of the E algebra of G tensored with O. And O refers to the structural sheaf on the pro-etale side. And so here I want to mention that this is pro-etale cohomology, but I also want to mention that this sheaf is just nu upper star of O1. So using the isomorphism proven by Scholze, one can easily calculate this. And then this will produce C vector spaces of dimension 2, while this will produce some BC spaces of dimension 1 and 2. And then using this non-trivial theorem of Corbet that the dimension is additive, one can then easily get this calculation there. And so the important upshot that I want to say is that one should view the complex LT as the Pro-etale cohomology of this local system, and thus coherent duality on the Fargues-Fontaine curve for C. What does it mean? I mean, it's we have some rigid analytic, right? One could actually also pass through the scheme. And then we just take like the internal dual with coefficients in O. And this coherent duality on the Fargues-Fontaine curve should be viewed as the correct duality. So why? Namely, as this example of P1 shows, one has to mix two different sorts of dualities, and one is QP duality. And so how does this work? So if this Pro-etale cohomology, say with L coefficients, turns out, so if this is a complex of finite dimensional QP vector spaces, then under this dictionary of viewing Pro-etale sheaves or as sheaves on the Fargues-Fontaine curve, then it corresponds to this complex on the Pro-etale side, tensored over QP with the structure sheaf on the Fargues-Fontaine curve, and the dual now on the Fargues-Fontaine curve by calculating the cohomology of the Fargues-Fontaine curve is just given by the dual of the complex, viewed as so I first take now the dual as QP vector spaces, and then I consider tensor this QP dual with the structure sheaf again. So now the other duality is coherent flavor, which comes from occurrences of the ground field C inside the cohomology. This is reflected as follows. So an occurrence of C, so of a C vector space, in the Pro-etale cohomology of L indicates a contribution of a skyscraper sheaf I infinity lower star of C, or more generally of some C vector space on the Fargues-Fontaine curve. And now the duality on the curve, I mean, it's a curve, which is like in the schematic version, just a Dedekind scheme, and then the internal home of a skyscraper sheaf O is just isomorphic to I lower star of C. And so now something important happens, namely there's a shift occurring. And so this shift is then actually responsible for this shift from the cohomology at the space in degree 1 dual to the space in degree 2. Now I have presented three very interesting and non-trivial examples. And so I want to mention our angle. So it's the theorem in progress. Okay, and the statement is the following. So there's a functor. X mapping to dx qp. And so what does this functor roughly do? So X should be a rigid variety. But actually, it's also allowed to be just any small V stack. X. And it associates to it some category. And what should it be, motivated by these examples? It should be the category of quasi-coherent sheaves on the relative Fargues-Fontaine curve associated to X. But that's only a heuristic statement, and I will make a more precise statement later. So for now, it should be seen as a category of solid quasi-coherent sheaves on the relative Fargues-Fontaine curve. X. So more precisely, I should make it right here the diamond. Okay. But it's an imprecise statement anyway. And so this functor should have the following properties. So first of all, it satisfies V descent and admits a six-functor formalism. So what does this mean? So for every bad X, this category DXQP has like a tensor product and also some internal homs. And then for every morphism F from Y to X, we have it in a junction pullback from DXQP mapping to dy of QP and push forward and so for every nice enough morphism from Y to X. And so here I just want to give an example. So any map between rigid analytic varieties. We have adjoint functors of an exceptional push forward from DYQP to DXQP, which admits an exceptional pullback. And base should satisfy usual compatibilities. So for example, base change for sheet. And so moreover, so this formalism should hopefully, like it's all in progress, it should solve this question that I raised in the beginning. So this means that for every x, we have a fully faithful functor. From, like I denoted dB lis x pro-etale QP. So it's a should be the full subcategory of the category of QP sheaves on x pro-etale whose cohomologies are local systems. And this should embed fully faithfully into this category dx QP. And so in particular, the cohomology between local for a QP local system can be calculated in this category dxqp. And so this functor, what should it do? Like heuristically, it should tensor a pro-etale local system with the like structure sheaf on the Fargues-Fontaine curve relative to x, but this formula does not make sense for every x. And then for a smooth map f from x to y, which is of dimension d, and it's a map of rigid spaces. The exceptional pullback should be isomorphic to the exceptional to the usual pullback tail twisted and shifted. And so we are aiming to prove this. And so I want to mention several relations. So first of all, this d-descent relates here to this fully faithful embedding. So one wants to have a theory which satisfies enough descent in order to capture pro-etale cohomology. When this functor f lower star, if say f is the morphism of a point, then this f lower star should just be the pro-etale cohomology. And so as part of his theorem, it's also the construction by known methods, I would say now, of compactly supported cohomology, namely, I mean that one takes some compactification and then takes some j, one has to construct some j lower shriek, but that's thankfully possible. But again, if f is morphism from x to a point, meaning say bar c, then this f lower shriek gives a version of pro-etale cohomology with compact support, which, for example, also should work, hopefully, in the case that x is, say, a closed unit disk. And then, so this isomorphism implies then a Poincare duality. i.e., the cohomology in the sense here, which does agree with the pro-etale cohomology in the sense in the beginning. Is isomorphic to the compactly supported cohomology of K and then dualized. But now this dual is taking place in this category, so it refers to this internal dual, and this duality by the construction will incorporate the coherent duality on the Fargues-Fontaine curve. And so I want to give, okay, I obviously cannot present any meaningful sketch of proof here. I just want to mention like the key difficulty in establishing the statement. And that one has to, one does, with this incredible thesis of Lucas Mann, actually this stuff can all be handled. The most difficult thing is the construction of this category. And because we want to construct this category and it satisfies v-descent, we can also use v-descent in order to construct it. And so it's sufficient to handle the case that X is a totally disconnected perfectoid space. And actually say of characteristic P, because the theory will only depend on the diamond and so on. And then in this case, we can set EXQP as a category of slightly modified solid quasi-coherent sheaves on the Fargues-Fontaine curve relative to X. And now this expression makes sense, but in order that it can satisfy these properties, one needs to prove the key technical statement, which is the following. So say we have perfectoid, affinoid space of characteristic of arbitrary characteristic Z, and then we want to map it to a category of almost modules, again of basically solid quasi-coherent sheaves or solid modules for A plus, that this satisfies v-descent. And here, the exact statement is that the affinoid perfectoid spaces that one is plugging in here should be plus bounded. And affinoid and perfectoid. And so this plus bounded roughly means finite p cohomological dimension. And actually, maybe only this finite cohomological dimension is actually necessary, because this notion of plus bounded in Lucas' thesis is not so direct.
Johannes, what is the subscript on the D?
This one?
Yeah.
That's a good question. So that these are modified solid quasi-coherent sheaves or solid modules. And so the theory of condensed or solid mathematics associates to any ring whatsoever some category of solid modules over A plus, but these have the problem that the compact generators are by definition, like if I have some profinite set S, then the projective generators of this category would be a huge co-limit over all morphisms where B over Z is of finite type. And so what we do, what we modify is we now take this co-limit and we complete it with respect to some pseudo-uniformizer pi. And then we have to analyze this category, and then, but this modification is then crucial in order to get this v-descent statement. But it also forces us to consider slightly different solid sheaves there, but actually say for nuclear objects, this does not introduce any difference. And so that's what I want to say about the sketch of the theorem, and I want to end with some drawbacks of this formalism, some deficiency, which hopefully in joint work with Fosco, Lebras, Rodriguez Camargo, and Peter, we can address, but that's nothing I want to speak about in detail. But I want at least to mention some drawbacks that this theorem has. So X should be smooth over C again, a rigid analytic variety, and these drawbacks can be listed. So the drawbacks are that this theory, it's quite abstract and it has no relation to differential form. And so Bosco, Gomez and Nizol, they have proven very nice results relating the Pro-etale cohomology to Yudokato cohomology and Iran cohomology, and this is not captured in this formalism. Then, in relation to some periodic bar conjecture, it has a drawback that it does not produce locally analytic representations on classifying stacks. Relatedly, there's another issue, namely the V bundles. They have received quite some attention in order in their role they play in the periodic Simpsons correspondence, and so this theorem also does not shed any light on periodic Simpsons correspondences. And then less direct, maybe deficiency could be the following, namely, it has also been, like Simpson initiated this theory of the RAM stacks with great success, which then also was taken up by Butler and Winfeld for periodic Hodge theory, and they have a very nice theory of prismatization. And this is also not how this formalism is constructed. Yes, and I think that's where I want to stop.
So this category of solid quasi-coherent sheaves, if you look at perfect complexes without the condensed words, is that a full subcategory?
Yes, and also on perfect complexes, they are automatically nuclear, and then they literally are just perfect complexes on the rigid analytic variety. So there one does not need anything solid, and one can in particular recover this descent result of perfect complexes.
And are those objects stable under smooth, proper direct images?
Yes, and that's a very good remark, because that's already visible in this example for the cohomology of 1v1 rigid of this local system constructed here, because there I wrote that these are BC spaces of some dimension. In particular, they are finite dimensional, and so the finite dimensionality that this example has is precisely that it's a perfect complex on the Fargues-Fontaine curve. And then by the sketch, okay, that is also part of this theorem in progress, but I think that we will also be able to prove this preservation under proper smooth forward, and then in particular implying that although the cohomologies are infinite dimensional, they still have some finiteness condition, which is that they correspond to perfect complexes on the Fargues.
So I understand roughly that your definition of this kind of derived category is that you take a hypercover by totally disconnected spaces, and then take the inverse limit of this construction of the stages. This is roughly the definition. And the descent result holds in particular for totally disconnected,
And actually, we also prove hyper descent.
For totally disconnect,
Yes. Yes, and then actually, like for this construction here, we prove hyper V descent. Then you can extend that sheaf to a sheaf on all small V stacks, and then you can also check the hyper descent then there.
But the thing about plus bound, I don't know
Like it implies that the FP cohomology on Z, the P cohomological dimension on Z is finite. like for etale sheaves. For etale sheaves, just on Z etale, I consider
Just say that someone says that and a priori you only know the value of this sheaf on totally disconnected space, but using this you can also evaluate it on some finite dimensional perfectoid disk over something totally disconnected.
yes. And that's critical in actually that this definition works.
So directly on such thing.
Because the usual perfectoid cover that one takes off a Fargues-Fontaine curve, it's not totally disconnected if one starts with a totally disconnected X. And so we really need the plus bounded, or anything sufficient in order to get it. Actually, just this morning, Lucas raised a bit the hope that we might only need that FP sheaves on Z etale have uniformly bounded cohomological dimension. But okay, we say plus bounded.
I mean, uniformly bounded an object of the side.
Yes, I mean, you can also phrase it in the way that like the R gamma for all etale sheaves is like uniformly contained in 0 D for some integer T.
But knowing it globally, does it imply it for a basis of the side?
Yes, because of the spanning property, if you have like a quasi-compact open immersion, then the J lower star is exact.
Yeah, but like perverse sheaf, we can also do this kind of realization.
What do you mean by perverse sheaf in this context?
So I don't have a definition, but I think there's naive examples of perverse sheaf, like maybe RA1.
I think I have not thought about if that makes sense here, but I thought that usually perverse sheaves are more defined in an algebraic context.
But the scale doesn't satisfy excision, does it?
It does not. So that's maybe also good.
Okay.
And what is the compactly supported cohomology on a closed ball?
Like how it's calculated, you have the closed unit ball over C. Then you have to embed it into its canonical compactification. But then you also have to like resolve it by totally disconnected spaces and so on. And this gets very complicated. And then in the end, on the Fargues-Fontaine curve, you have to use the like a base change of the J lower streak functor in solid quasi-coherent cohomology. And so this is again something explicit, and so we have not yet done this calculation in detail. What's the result? I mean, it's a complicated thing.
Why can't you use the definition we use for time spacing?
I suspect that it does not work for such thing because we don't have this cofinality property of closed and open quasi-compact sets.
So here everything is quasi-compact. It is quasi-compact. So
And therefore, the duality does not work for this previously defined version of the compactly supported Pro-etale cohomology, which was defined by some co-limit over U inside X quasi-compact.
Don't take just remove the disk.
But then don't I have to use some ad hoc space in the best route?
what is which definition?
There is a ghost circle on the boundary.
I think for these spaces, this does not apply yet.
This fully faithful functor from DB list to D, can you extend it Is there such a thing if you extend this source a little bit to include like skyscraper of QP on the point?
Skyscraper of sheaves. So, like, I mean, when you are asking about the Pro-etale cohomology of rows, right? And then I think you are asking, I think, just about perfect complexes in this category.
I think there are two things you could do. I mean, you could first use the same functor on a point and then apply the lowest R. But then you run into get the excision issue that you probably want. You have an open and complementary closed, and usually you have an exact sequence. Taylor Schrieg, lowest R. Realizing all three terms individually via the six factors. Yeah, I mean, treating them as local systems on these individual pieces and then applying the corresponding functors. In the big categories, I don't think you get an exact triangle anymore.
Yes, I think so. I think I misinterpreted your question. You were speaking about the I lower star or QP. Yeah, okay, this I don't know. I'm skeptical. Like,
is this category DXQP? Is that compactly generated?
for general X, that's a very subtle question because it's only defined so by descendants on. But in cases where you have some plus boundedness assumption, then I think it is.
So for Gaussian coefficients, there is no, I mean, it's completely different. That is that there you don't have any subtlety of how to define what is supposed cohomology. It is the only way is using the canonical compactification.
But we also do the same here with QP coefficients. And I actually think like that's also part in progress, but actually we can replace the QP by ZP. But then of course one cannot use the Fargues-Fontaine curve anymore. But then what we want to investigate if one can take the space Y 0 infinity with 0 included and then consider phi modules on that space. And if that maybe gives formalism which does work for ZP coefficients.
Any other questions? Okay, you have no questions, let's thank the speaker.